Hi, welcome back for session 3.3. Session 3.3, we're going to do applications of linear programming problems. So basically in this session, what we're going to do is we're going to take what we took a look at in 3.1 and 3.2, linear programming, and we are going to make it happen starting at the bottom and building to the top. So in section 3.1 and 3.2, they gave us everything, meaning they gave us the constraints, they gave us the objective function, they gave us all of that. In this one, we're just going to start at the bottom. We're going to build the constraints, we're going to build the objective function, we're going to graph the feasible region, we're going to find the corners, we're going to evaluate the objective function in the corners, and we're going to figure out the answer to the problem. All right, our first example is going to be this one right here. We're going to go back to take a look at that Happy Ice Cream Cone Company problem. All right, so let's go ahead and get started. I've already read the problem, but I'll read it again just in case. Happy Ice Cream Cone makes cake cones and sugar cones. Both of us must be processed in the mixing department, baking department. So I have a mixing department and a baking department. Manufacturing one batch of cake cones requires an hour in mixing and 2 hours in baking. Sugar cones requires 2 hours in mixing and 1 hour in baking. Each department, that's the mixing and the baking, at most 12 hours. Each batch of cake cones earns $47 profit. Sugar cones earn $63 profit. Maximize profit. All right. So I see what my objective is. My objective is to maximize profit. So then Z, my objective function, needs to be the profit function. So let's see, what is that going to be? That's going to be $47 for every batch. Oh wait, you know what I didn't do? I'm ahead of myself in my own head. I need to find my variables. So I'm going to say that X is equal to the number of batches of cake cones, and Y is going to be the number of batches of sugar cones. And then I can write my profit equation. Now I can say that Z is equal to $47 times the number of batches of cake cones plus $63 times the number of batches of sugar cones. Okay. All right, so I've got my objective function. Now I can start working on my constraints. My constraints are my limitations. My limitations are the baking department and the mixing department, because I know that I cannot exceed 12 hours mixing and I cannot exceed 12 hours baking. So then what goes over here needs to be the time that it takes to mix and to bake. Well, mixing requires 1 hour for the cake cones and 2 hours for the sugar cones, so 1x plus 2y. And then baking is, let's see, cake cones 2 hours baking, and sugar cones 1 hour baking, so 2x and 1y. Now, it also makes sense to make the following statement. The non-negative conditions would apply here, that x and y can't be negative, and then we can go from there. So now that I've got my objective function figured out, I've got my constraints figured out, I've labeled my non-negative conditions, so I can go over here and I can make a sketch of my feasible region. Okay. I know that my first constraint is going to have x-intercept of 12, y-intercept of 6. And I know my second constraint is going to be those flipped. That is, the x-intercept will be 6, and the y-intercept will be 12. So both of these need to go to 12, and then that would be 6. There's 12. There's 6. I'll graph the first one in purple, and so that goes from 12 on the x to 6 on the y. We want less than, so we want this side down here. I'll graph the second one in green. Actually, you know what? No, I don't like that green for the graph. I'm going to use the red. And that goes from 6 on the x to 12 on the y, so it goes up like this. And then we want the less than, so we want this side over here. I could test a point, but I'm pretty good at this, so I know what I'm doing. So I won't test the points, but I could. I've got 3 corners that I care about and one that's there just because. All right? So I will call them A, B, C, and D. A is the corner 0, 6. B is the corner I don't know yet. C is the corner 6, 0. And D is the corner 0, 0. Okay. How do I find corner B? Well, corner B is the intersection of the red line and the purple line. So it's the intersection of x plus 2y equals 12 and 2x plus y equals 12. Okay. So I'm going to solve this system any way I want. So I'll bring up my calculator because I'm lazy and I love my calculator. I'm going to put this matrix, this augmented matrix in here, and I'm going to Gauss-Jordan this thing. So let's see, that matrix is going to be a 1, and then a 2, and then a 12, and then it's going to be a 2, and then a 1, and then a 12. And then I quit out of there. And I will RREF that matrix, and I get that x is 4 and y is 4, or that that corner B is the point 4, 4. So now what I need to do is I need to evaluate the objective function in each corner. So at corner A, what's the value of z? Well, my objective function up here in blue is 47x's plus 63y, so it's going to be 47 times 0 plus 63 times 6. 63 times 6 is 378. 63 times 6, 378. And these are dollars because it was $47 and $63 per batch, respectively. Now I'll do corner B. At corner B, the value of z is going to be 47 times 4 plus 63 times 4. So 47 times 4 plus 63 times 4, and I get 440. And again, these are dollars. Okay. Now I'll find corner C. Corner C, the value at corner C is going to be z equals 47 times x, which is 6, plus 63 times y, which is 0. 47 times 6, $282. Now I can't forget about D, even though I know it's going to be nothing. 47 times 0 plus 63 times 0 is 0. Which makes sense because if you make nothing, you earn no profit. Now I stare at this for a second and I try to figure out which one's the biggest. And it looks like 440 is my largest. So then the final answer to this problem is they should produce 4 batches of each type, because it's 4 of each, right? And they will earn, so $440 profit. Okay. So linear programming. Somebody wants to do something. They have an objective, in this case to maximize profit. They have constraints, that is how many hours they can spend mixing and how many hours they can spend baking. There's a bunch of different ways that this problem could play out. Every point in the feasible region is a potential winner here. We're looking for the one that makes it as big as possible. We're looking for the one that maximizes our objective function. So we test each corner because of the corner point theorem. The corner with the biggest value here, because we're maximizing, is our winner. And it looks like 4 batches of each wins. $440 profit. I don't think I have enough time to do this one in this video, so I'm going to stop this video here. We'll come back. I'll do this problem right here in video number 2.